Hi, I'm Fishing Paul and welcome to the distiller tutorial video. This video is part of a series of tutorials on NuclearCraft Overhauled. In this video, we'll explain how a distiller works and then design and build a heavy water production facility. The distiller is an NCO multiblock whose purpose is to distill fluids. Its primary use is to make heavy water for NCO, and for those of you who have come here from the QMD tutorials, we can also use it to distill liquefied air. To distill fluids, the distiller needs to have separation layers inside of it. There are two kinds of separation layers that you can use: the packed sieve layer and the tray sieve layer. This is a packed sieve layer. It consists of a layer of identical sieve assembly blocks. A tray sieve layer is a 2-block tall layer consisting of tray sieve blocks with identical sieve assembly blocks on top, like this example over here. For the purposes of this tutorial, this layer is going to be called a sieve layer, and this layer will be called a tray layer. The following rules govern layer placement. The layer must cover the entire horizontal cross-section of the distiller. You can use just one type of layer or both types. The layers can be touching each other, no need to have air gaps between them. If the recipe involves more than two liquids, either as inputs or outputs, you need one tray layer per additional liquid. If in doubt, check the recipe in J, where it says the minimum required tray count. The order of layer placement doesn't matter. Finally, you can optionally use reflux units and liquid distributor units in the ceiling and reboiler units in the floor of the distiller to increase process speed. The distiller has two main design equations: the speed multiplier and the power multiplier equations. The speed multiplier affects the distiller's process rate, which is expressed in millbuckets per tick for one input or recipes per tick for two inputs. The process rate is simply the base process rate calculated from the base recipe stats from J times the speed multiplier. The speed multiplier is equal to the area times the layer efficiency times 1 plus reflux bonus times 1 plus reboiler bonus times 1 plus distributor bonus. Many terms, let's take them one by one. The area term is simply calculated from the distiller's dimensions. The layer efficiency is calculated from the number and the types of the layers. If you have only sieve or only tray layers, the layer efficiency is simply the sum of the efficiencies of each individual layer. If you have both sieves and trays, the layer efficiency is equal to the number of sieve layers times the total efficiency of tray layers plus the total efficiency of sieve layers, and all of that divided by 1 plus the number of sieve layers. For the final three terms, we need to calculate 5 ratios that we use in these terms: the liquid ratio L, the gas ratio G, the reflux ratio F, the reboiler ratio B, and the distributor ratio D. L is equal to liquids divided by total fluids, G is gases divided by total fluids, F is equal to reflux units divided by area, B is equal to reboiler units divided by area, and D is equal to distributors divided by area. The reflux bonus is equal to G times F, reboiler bonus is equal to L times B, and distributor bonus is equal to D divided by 1 plus the number of tray layers. Therefore, reflux units are most effective in recipes with many gases, reboiler units are most effective in recipes with many liquids, and distributors are most effective with no trays and as few liquids as possible. The power multiplier affects the distiller's power draw and is much simpler to calculate. The power draw is just the base power of the recipe times the power multiplier. The power multiplier is equal to the area times the total layers, sieves plus trays, plus the reboilers. This means that the power cost scales linearly with the number of layers, and reboilers can increase the process speed at a decent energy penalty. Having explained the design equations, we can now design a distiller. As promised at the start of the lesson, we'll make a heavy water production facility. In NCO, water can be enriched to heavy water in 3 steps: 25%, 50%, and 100% pure heavy water. I will design a facility which produces directly 100% heavy water, since otherwise I must electrolyze the less pure heavy water to separate it from water, and this is expensive and slow. The overall process is 250 millibuckets of water plus 750 millibuckets of hydrogen sulfide makes 250 millibuckets of heavy water and 750 millibuckets of depleted hydrogen sulfide every 800 ticks. The hydrogen sulfide regeneration recipe is 250 millibuckets of depleted hydrogen sulfide turns to 250 millibuckets of hydrogen sulfide every 400 ticks. We therefore need to make 3 identical distillers for water enrichment, and one distiller that is 1.5 times larger for hydrogen sulfide regeneration, since it needs to process 3 times the inputs at twice the speed. Let's aim to produce one heavy water moderator every 2.5 seconds, which corresponds to 20 millibuckets per tick of heavy water. The speed multiplier needed to achieve that is simply the desired production rate divided by the production rate at speed multiplier 1. Dividing 20 by 250 over 800, we get 64. Using the speed multiplier equation from the previous chapter, substituting an area of 16, which corresponds to a 4x4 distiller, a layer efficiency of 400% and 0 for the bonuses, we can achieve 64. And following the same train of thought, we can make the hydrogen sulfide regenerator with an area of 16 and a layer efficiency of 600%. To keep costs low, I'll use steel sieves, which only have 80% efficiency, and thus we need to get a 1.25 multiplier from somewhere to offset that. There are three ways to get that multiplier: bigger distiller, more layers, or the use of reflux units, reboiler units, and distributors. To make a more complete tutorial, I'll use the third option. We have 4 fluids, 2 of which are liquids and 2 of which are gases. Therefore, L and G are both 50%, so reflux and reboiler units are equally effective. However, since reboilers increase the power cost, they are eliminated. Since we only have 2 liquids, we don't have to use trays, so distributors are at their maximum possible efficiency. So let's use these in favor of reflux units. This also benefits us since sieves take up only 1 block of height, making for a shorter distiller. To calculate the number of distributors we need to calculate 1 plus d divided by 1 plus 0, since we use only sieves, and that should be equal to 1.25, which results in d equals 0.25, and therefore 4 of the 16 blocks in the ceiling of the distiller must be distributors. Finally, we need to calculate the number of layers. Since we're using only sieves and only one kind of sieve, the layer efficiency is simply 80% times the number of sieves. The speed multiplier equation is simply 64 equals 16 times 80% times sieves times 1.25, and solving for sieves we get 4. Following the same design philosophy for the hydrogen sulfide regenerator, we get that it needs 6 sieves. For completeness sake, let's calculate the power consumption. Here's the power consumption equation as a reminder. For our water distillers, the base recipe cost is 5 RF per tick times 16 area and 4 layers makes 320 RF per tick per distiller. For the hydrogen sulfide regenerator, the base recipe cost is 10 RF per tick times 6 in area and 6 layers makes 960 RF per tick. So in total, we need 320 times 3 plus 960, 1920 RF per tick to run our entire setup. Therefore, we need to build 3 4x4x4 distillers with 4 steel sieve layers and 4 distributors, and 1 4x6x4 distiller with 6 steel sieve layers and 4 distributors. Time to put on our hard hat. I'm going to build the distiller step by step using schematica. In the background, I've already built 2 of the water distillers and the hydrogen sulfide regeneration distiller. First, we need to make the frame. As with all NCO multiblocks, when we give dimensions, these dimensions refer to internal dimensions. So for a 4x4x4 distiller, we will need to make a 6x6x6 frame. This is a frame, I'm going to print it. And then, in the bottom, we can place reboiler units, but this design does not require any reboiler units, so we'll just skip this step. And then I'm going to place the separation layers. We said that we would wanted to place 4 steel sieve assembly layers, so this means we will just place a solid 4x4x4 cube of steel sieve assembly blocks. The next step is to place the ceiling, which consists of 4 distributor blocks and 12 casing blocks. The distributors can go anywhere on the ceiling, it doesn't really matter in what position they are, but you have to have 4 distributors for the design to work properly. I decided just to put all of them here in the corner. You can just put them wherever you want, but they have to be on the ceiling. And for the final touches, we need to place the final functional blocks of the distiller, the controller, the power port, and 4 process ports, which is where the fluid input and output occurs. Using the multi-tool on the ports, we can set which fluid is input or which fluid is output. And now, I'm going to set up off camera the connections and the ports to the other distillers, and I will see you after the cut. Alright, so now all of the distillers are hooked up, and using the thermal series multi-tool, I can see that the average in and out is 20 millibuckets, which is 20 millibuckets per tick. We have successfully designed our facility to produce 20 millibuckets per tick of heavy water. And now let's go to the outro. So, recap. The distiller is a multiblock which enables us to split fluids into several other fluids, notably to create heavy water and distill air into various useful gases for QMT. It is built out of machine casing blocks, and it uses sieve assembly and sieve tray blocks to distill fluids. Its process speed and energy depends chiefly on the number of layers and its size. Finally, we applied the above principles to make a heavy water production facility that is able to produce 20 millibuckets of heavy water every tick. I hope you found this video helpful, and I expect to see you in my next tutorial. Goodbye.